Hey students, welcome back. This is Torres, Bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, please send me an email so that I can try to help in some way. So lucky you get to hear my voice for another lecture. But the best part is we will be continuing our work with estimating population proportions with confidence intervals. Yay! Let's review a few basics. If you recall, we keep talking about trying to find the truth within the sample that we've been able to gather from our population of interest. The information about the population is called the parameter. The parameter is the truth. It's what's really happening within a group of people or animals or medications or whatever it is, right? It's the true effect. We will never know what the truth is with only a sample. We can make some educated guesses, some inferences about what the truth may be based on what we've learned about the sample, but we will never really know the truth. The only way we can know the truth is if we tested everybody within the population. What we can do, however, is we can have a really good estimation of the truth to some degree of confidence. The range of plausible values for a population parameter is called a confidence interval. And that interval expresses the level of confidence that we have that that interval will have the population parameter. So in this diagram, for example, this blue dot is what we estimate the population to be based on our sample. This red dot is what we don't know. If we had some higher being that knew what the true value was, it would exist here. We're trying to guess in the dark where that red dot is, in essence. Here we have a confidence interval of 95%. So what we can say is we estimate that the true population parameter is this blue dot, the value that aligns with this blue dot. And we can say with 95% certainty, not 100% certainty because we don't know the truth, but we can say with 95% certainty that the true population proportion lies within this range between this lower bound and this upper bound. That's where we think the truth lies. Most of the time will be correct. 95% of the time will be correct. But then there's that small 5% that we will be wrong. The relationship between the confidence level and their interval width is clear to see. Here we have a 68% confidence interval. Here we have a 68% confidence level. Notice that the width of this interval is much smaller, right? It's shorter than the 95% confidence level. This is a little bit longer. It takes up more of this number line. Notice here where the confidence level is 99.7%, the width of the interval has increased even more. Here, when there is a 99.99% confidence level, the interval width almost takes up the entire number line. This is important because if we choose a confidence level, say 68%, we have very little room for error. Say we believe our sample statistic is here, 0.5. That is what we estimated the population parameter to be based on our sample, right? We're trying to guess, in essence, where this red dot is. We can't see this red dot, it's hidden. Well, with a 68% confidence interval, we're only going to accurately predict that the truth is within that interval width approximately 68% of the time. Here, if we look at the 99.7% confidence level and this interval width, here we would have been able to say with 99.7% certainty that the true population parameter exists here. See how this is wider? There is more of a chance that the true population parameter will be captured within that larger net. Okay, so you're giving yourself this wider net so you have less room to make a mistake as far as where the true population parameter actually lies. Those numbers, 68, 95, 99, come from our normal curve. They come from the empirical rule that states that if and only if your distribution is approximately normal, that approximately 68% of all your values will exist within one standard deviation before and after the mean. if and only if your distribution is normal, then approximately 95% of all values will exist within 2 standard deviations before and after the mean. And if your distribution is normal, and only if your distribution is normal, then approximately 99% of your values will exist within 3 standard deviations before and after the mean. Note that although I use the word mean here, and we've been working with proportions, that instead of the mean being in the center, the sample proportion or the population parameter proportion would be here in the center. In order to calculate the confidence interval, you need the information about where you estimate the true population to be, right, based on your sample. And you need to calculate the margin of error so that if you add that margin of error to your estimate, you will have the upper bound. And if you subtract that margin of error from your estimate, you will have a lower bound. So it'll give you 2 raw scores within which you can expect to find the population parameter. Since we're using an estimate of a sample proportion, we're going to use the standard error to describe that spread. And we're also going to use the z-scores that are aligned with the 68, 95, 99, etc., so that we know exactly how much of that standard error will be necessary to find the lower bound and the upper bound on either side of the estimate. So we are going to be, like I said, here's the standard error formula. If we have the true population proportion, then we can find the standard error based on the size of our sample. And if we have a sample proportion, then we can estimate the size of the standard error. A few lectures ago, we talked about trying to increase precision. And increasing precision, and one way to increase precision is to use the more precise versions of the z values to calculate the margin of error. So if you recall, 95% is about 2 standard errors. When we were working with it back in the day and using the empirical rule, about 2 standard errors is what we would approximate 95% of the values to exist. However, 2 is just a rounded off number. It really is 1.96 with a bunch of numbers after it. But we're going to use this multiplier, and these are called multipliers. We're going to use this multiplier times our standard error to find the margin of error. And then if we add that margin of error to the proportion, to our sample proportion, then we can find the upper bound. If we subtract it, we can find the lower bound. So let's do a few more examples where we're kind of putting everything together that we've learned so far. In order to be successful with this, you're going to need just paper and pencil, a calculator. I use Google Calculator, but you can use whatever you like. You need some sort of technology to calculate probabilities. I'm going to be using StatCrunch. And you need the multipliers for the different confidence level intervals, and there is a copy of that in the description box below. Also, if you have a probability diagram, that's helpful. Again, there's another document linked in the description box below that does have the probability diagram. Okay, so let's start with this example. It has to do with intelligent life on other planets. So it says, a poll of 1,000 randomly and independently selected Americans found that 38% believe that there is intelligent life on other planets. A, construct a 95% confidence interval for the percentage of all Americans who believe there is intelligent life on other planets. And B, would it be plausible to conclude that 40% of Americans believe in intelligent life on other planets? Okay, well, let me go over to Zite Board and copy that into that. So here is the Zite Board. I went ahead and copied that example that we were talking about into the Zite Board. As you can see, it's just the same exact thing. And let's start by looking at if it discusses whether this distribution is normal or not. It does not state whether the distribution is normal, so I need to check the conditions of the central limit theorem to see if we can assume that the distribution is normal. So the first condition is that the sample is random and independent, and we see that it states that clearly in the problem. So check. that condition is met. The next condition is the size of the sample. And I need to make sure that my sample size times my expected proportion is greater than or equal to 10. And these would be the successes. I also need to make sure that the number of failures is greater than or equal to 10. So I've got my sample size is 1,000. My expected parameter is 38%. So let me go ahead and write that as a decimal. And I'm going to see, let's see how many of these 1,000 people are expected to believe in intelligent life and other planets, on other planets. So here's my n. I've got 1,000 times 0.38. And I'm going to go ahead and pull my calculator over here. Okay, so here's my calculator. 1,000, 1,000 multiplied by 0.38 equals, and I got 380. So 380 is greater than or equal to 10. Does that check out? Yes. Now, if 380 are what I expect of this sample, right, of these Americans to believe that there is intelligent life on other planets, then everybody else, it would be expected not to believe on life on other planets. So I can just go ahead and subtract 380 from 1,000 and get 620, but I could also just do it using the calculation here. So 1 minus 0.38 is greater than or equal to 10. And if I were going to go ahead and pull up my calculator again, okay, so notice here I have 1,000 multiplied by the difference of 1 whole and 0.38, and I should get 620. So this is 620. Is 620 greater than or equal to 10? It is. So both conditions of sample size are met. This is a great big giant check. The last condition is the condition of population size. And for that one, I want to see that the population, big N, is at least 10 times bigger than my sample size. So I need to think to myself, is all Americans bigger than 10 times 1,000? I'm going to scooch this up some more. I never scooch up enough. Scooch, scooch, scooch. Okay, so here is this. And are all Americans, which is my population, is there more than 10,000 Americans? Yes, definitely. So we're going to go ahead and hit check. So with these conditions, with these tests right here, these few calculations, I can say that according to this, all conditions of the central limit theorem are met. Therefore, I can assume normality. So I have a normal distribution. So let me go ahead and draw out my normal distribution. I'm going to go ahead and again make myself a little bit, give myself a little bit of space and draw my normal curve. Okay, so here is, it's my little dog barking. If you heard my dog bark, comment down below. Okay, so here is my sad little curve. This one came out kind of messed up. Okay, and I'm going to go ahead and write my z-scores right here. And I'm going to scooch this up because I'm starting to get I don't know if it's because it's to the bottom or what, but I'm starting to get a little bit off. So, okay, so here is our sample proportion is that is 0.38. Okay, so that's our sample proportion. Now I have to find this distance, and I can find that distance using the standard error formula. And this is actually, it says a poll of 1,000 randomly and independently selected Americans found that 38% believed in life on other planets. Okay, so here's the poll information. We can find the standard error for this poll by just plugging everything in. So here I have 0.38 multiplied by the difference of 1 whole minus 0.38, and for a sample size of 1,000. Let's figure out what my standard error should be. So I've got 0.38 multiplied by the difference of 1 whole and 0.38 close parenthesis equal. That gives me my numerator. Now I'm going to divide by my sample size. And I have everything underneath the radical. And now I can take the square root by just hitting the square root sign and then hitting answer. And I will get that my standard error is 0.0153. And notice again, this has a huge, notice here that the standard error goes out many, many decimal points. So when I round this, and I'm just going to go ahead and round it to 0.02 or 0.015 or 0.0153, I'm still cutting off a lot over here. So all this is going to lead to error ultimately. Okay, so I'm going to go ahead and write this here as my standard error is 0.0153. And if I rounded this just to make this a little bit easier on me, I could say that this is kind of close to 0.02, right? Because I could round this up to 2. So this distance right here, this standard error, and I'm going to zoom this in now to make this easier for me to write on. This distance right here is going to be 0.02. Now, I'm not dealing with precision, and I'll tell you why. Here, this diagram is just giving me some reference so that I can look at it. Okay, so that I'm seeing what is happening with my whole entire calculation. I'm seeing how everything is related, and drawing the normal curve and actually lining it up each time gives you a very clear indication of what you're looking for when you're done, when you've answered all the questions, etc. So here's 0.02. This is going to be another 0.02, right? Another 0.02. And the opposite direction, this would also be 0.02, this would also be 0.02, and this would also be 0.02. So if this is 0.38 and we add another 0.02, then we're going to get 0.4, right? And if we add another 0.02, we're going to get 0.42. And this can also be that. And if we add another 0.02, then we're going to get 0.44. And in the opposite direction, if we've got 0.38 and we subtract 0.02, then we're going to get 0.36. And subtracting another 0.02 is going to be 0.34. And subtracting another one is going to be 0.32. So I'm lining this up here to see kind of what's going on, right? And these are this is the information that I got from the sample that I was working with. Okay, awesome. So the question asks what? It says, construct a 95% confidence interval for the percentage of all Americans who believe there is intelligent life on other planets. Okay, so I need to find the 95% confidence interval for this. 38 is in the middle, and I need to find, I'm going to do this in blue. 38 is in the middle. I know this distance right here is 68, so approximately from here to here, approximately, is 95% of all values. I need to find what this lower bound is and what this upper bound is. Now, remember, I have rounded. This is my actual standard error. This is what I use to construct my diagram to keep things straight. Normally, in the past, we've used +2 and -2 to show the z-scores that correspond with 95% of the values existing within 2 standard deviations before and after the center value, either the proportion or the mean. But this 2 was also an estimate. So when we rounded the 2, positive or negative, we rounded it, we are also contributing to error. We're lacking precision. So I'm going to go ahead and keep the standard error precise by not rounding it. And I'm also going to use the confidence interval multiplier for 95%. That is 1.96. If you've forgotten, the confidence interval for 95% is 1.96 because it's a given, right? Let me show you. So here are my multipliers. It says for 95% confidence interval level, I can use 1.96. So this is strictly just a given right here. Okay, so I need my lower bound and my upper bound. So here is my 0.38. I need my z-score multiplied by my standard error, right, to get my margin of error, and then I need to add it to 0.38, and then I have to do the same thing. Take that same margin of error, which is the z-score multiplied by the standard error, and I need to subtract it from 0.38. So let's figure out what the z-score times the standard error is so that I have my margin of error. So I've got my margin of error here. Here's my calculator. Okay, I'm going to go ahead and clear this out. I've got my z-score is 1.96, and I'm going to multiply my standard error, which is right here, which is 0.0153. Okay, I rounded a little bit, but not as much. And I'm going to get that my margin of error is 0.0299. So margin of error it's going to be the same on both sides. Now, if I wanted to, I think this is 8. If I wanted to round this, then I could just round it to the MOE being 0.03. It's very, very close to 0.03. My margin of error is going to be the same because here I'm going to multiply that same z-score, 1.96, by the standard error again, which was 0.0153. I'm going to do it again over here. So 1.96 times 0.0153. If I pull up my calculator again, 1.96 times 0.0153, 0.0153, yes, I still have that same number, which is 0.02998, and I can round it to 0.03. So it's going to be the same. So the margin of error on this side, I'm going to subtract it, and on this side, I'm going to add it to 0.38. So here, I'm going to have 0.38 plus my MOE, which is 0.38 plus 0.03, and I'm going to get 0.41, and that is my upper bound. And on this side, I'm going to subtract it. I'm going to subtract 0.03 from 0.08. So here I'm going to have 0.38 minus 0.03, and I'm going to get 0.35, and that's going to be my lower bound. Now, let's compare it to this. Remember here I rounded. I was off by quite a bit. I was off by a whole 0.01. Here I just used 2, but what makes it nice is I still have something that I can refer to. All right, so let me scooch this down. I want to write this out really nicely. Okay, what can I say here? I can say that according to my sample, I can say with 95% certainty that the true population parameter of people that believe in intelligent life on other planets is somewhere between 35% and 41%. This gives me my answer to problem A, or question A. For question B, it says, would it be plausible to conclude that 40% of Americans believe in life in other planets? Yes, it's pretty plausible. It's within this area right here. It wouldn't be difficult to believe, so you can say it is plausible. Just as in the last few videos, I have all the PowerPoint slides, again, Google Slides are linked down below, that have the calculations written out for you to review. Now, this is a lot of calculations. One thing you can also do is you can use StatCrunch to take care of a lot of these calculations for you. So let me show you how to do that real quick. So I'm going to go ahead and go into StatCrunch. Here I am in StatCrunch. I'm going to go into here to stats. I'm going to go to proportion stats, one sample, and I'm going to go to summary. Okay. Number of successes, we had calculated that here. Our number of successes is 380. So we have 380 successes. Number of observations is sample size, 1000. And here it'll say, do I want a confidence interval? Yes, I do. I want a confidence interval 95%. And I want to go ahead and compute. What do I get? This is really nice because look, it'll give me my count, my successes out of the total. It gives me my sample proportion. It calculates the standard error. It gives me my lower bound, which if you recall, it was 0.35, but we had rounded it. So this is what it really is, 0.34991599. That rounds to 0.35. And this is our upper bound. Here they call it the upper limit. That is, we had it was 0.41. Here they're saying it is 0.41008,401. We rounded it. They did not. So theirs is much more precise. But like I said, it makes it kind of nice because you have this tool to be able to try to avoid all the little calculations. Let's do one more example, but this time let's do it with a different confidence level. We've used 95 a couple times already. So it says, a political consultant randomly surveys 300 voters in a district to see how many intend to vote for a certain candidate. Of the 300 voters surveyed, 165 indicate they will vote for the candidate. Using a 99% confidence interval level, should the consultant predict that the candidates will win the election, why or why not? Okay, so same thing. I'm going to go ahead and go into Zite Board. I've pasted this into Zite Board, and I'm going to go ahead and start checking the conditions of the central limit theorem. So CLT 1, random and independent. Well, it says randomly. It doesn't say independently. I'm going to go ahead and give it the benefit of the doubt and say check. 2, they surveyed 300 people, so that's my sample size. And of those, 165 said that they were going to vote for this candidate. So my sample proportion is going to be 165 out of the 300. So let me go ahead and calculate that out. So I've got 165 divided by 300, and I get 55%. Now that I have my proportion, I can check for my sample size condition. So sample size has to be the sample times the proportion has to be greater than or equal to 10. I have 300 multiplied by 0.55, and I'm going to get, here's my calculator again, 0.55 times 300 is going to be 165. Well, it just went backwards. Equals 165. Is 165 greater than or equal to 10? It is. Those are my successes. Well, either people are going to vote for this candidate or they're not. So if 165 did vote for the candidate, then the difference between 300 and 165 will be the people that did not vote for the candidate. So I can do this a couple different ways, and this time I'm going to go ahead and just do it this way. I'm just going to say that the failures are 300 minus 165. And if I put that into my calculator, just clear this out to show it to you, 300 minus 165, I get that 135 will vote for the candidate. So 135, is that greater than or equal to 10? It is. So here I just subtracted the successes from the total to get the failures. Now, I just want to show you how this is no different than calculating it out with the formula. So the formula is the sample size multiplied by 1 whole minus the proportion. So the sample size is 300. I've got 1 whole minus 0.55. And if I get my Google calculator out here, I'm going to go ahead and clear this out. 300 multiplied by parenthesis 1 minus 0.55 close parenthesis, I also get 135. So again, you can do it either way. You just want to make sure that it makes sense. You're going to pick which way makes sense to you. So is 135 greater than or equal to 10? It is. So that condition is met, completely met. The sample size condition is completely met. Next, population condition. The population size has to be greater than or equal to 10 times the sample size. And these are voters. So think of all voters has to be more than 10 times 300. And 10 times 300 is 3,000. So is there more than 3,000 voters? Yes. So at this point, all conditions of the central limit theorem have been met and normality can be assumed. Boom. Perfect. Let's scroll this down. Okay. Now let's draw my diagram. Make myself a normal curve. P hat is 0.55. These are my z-scores, my estimated z-scores. 0.55 is in the middle. I need to find this distance, and I can find that distance using my standard error formula. So I can estimate it using my standard error formula. Here's my standard error formula. Plug everything in. 0.55 times 1 minus 0.55 divided by 300. Great. Bring this over, clear it out. 0.55 times parenthesis 1 minus 0.55, close parenthesis. I have what's in the numerator. Now I'm going to divide by my denominator, which is 300. Now I have everything underneath the radical, and now I can take the square root of that number and find that my standard error is 0.0287. Okay, and just to round it, I can say it's just 0.03. So I'm going to go ahead and round this as 0.03 and mark this off for myself. So here is my standard error. I'll just put it in red. Okay, I'm going to add it going this way, so 0.58, 0.61, 0.64, and in the opposite direction I'm going to subtract. So 0.52, 0.49, and 0.46. Okay, and I want my 99% confidence interval level. So it's going to be something like this. All right, let's scooch this up. Remember, just to remind you of the question, it wants 99% confidence interval level. I need to find my multiplier for that again, and I'll just bring that over here again. Remember that there is a copy of the multipliers, commonly used multipliers, in the description box below. I'm going to bring this over here. So here's my confidence level information. I'm looking for a 99% confidence interval level. So the multiplier that I need is 2.58, and it's right here. Great. Okay. So what is this saying? It's saying that I need this 0.55 in the center, this one right here, and I need to find this distance so that I can find the raw score that matches with this margin of error, and I need to also do the same thing for the other side. These two margin of errors is going to give me my confidence interval. So on this side, I need my multiplier times my standard error to get my margin of error. So my multiplier is 2.58. My standard error, I'm going to not round it this time, is going to be 0.0287. And once I get this number, I'm going to add it to 0.55 to get the upper bound. Same thing is going to happen on this side. I'm going to get the z-score, and I'm going to multiply it by the standard of error to find the margin of error. It's the same number that's going to be here, 2.58, which is my multiplier that I got from this table, multiplied by my standard error, which is 0.0287. So let's figure out what that number is. Clear this out. 2.58 times 0.0287 equals, my margin of error is 0.074. So MOE equals 0.074. And it's the same thing on this side. MOE equals 0.074. 0.474. On this side, I'm going to add the margin of error to 0.55. So 0.55 plus 0.074. And on this side, I'm going to subtract it. 55 minus 0.074. I'm going to bring over my calculator. 0.55 plus 0.074. 0.624. That's going to be the same as 62.4%, or my upper bound. So on this side, we've got 0.55 minus 0.074, and we're going to get 0.476. That's approximately the same as 47.6%, and that's your lower bound. And if we look here, we were supposed to get 46, we got 47.6. Difference came because of rounding. And up here, we were supposed to get 64, and we got 62.4, but again, the difference happened because of rounding. So there's like that error that happened with the rounding. So what does that mean? That means that according to this scenario where it talks about candidates, I believe. Okay, we don't know what percentage of the population will vote for this specific candidate. However, according to the sample that has been taken, it can be said with 99% certainty that the true population proportion exists somewhere between 47.6% and 62.4%. That means that between 47.6% and 62.4% will likely vote for that candidate, and that can be said with about 99% certainty. The last part says, using the 99% confidence interval, should the consultant predict that the candidate will win the election, why or why not? I mean, you need over half to win. So because here at the low end, the candidate will lose, and here on the high end, they'll win. So really, according to this sample, there's no way to know with any degree of certainty that that candidate will win the election. They just know that they'll receive between these two percentages of the vote. If they get above 50%, awesome. If they don't, too bad. The same calculations are here for you to use. I want to go into StatCrunch again, just to show you how this would work. You can go into Stat, Proportion Stats, One Sample with Summary. The number of successes was 165, right? Because we had 165 people of the 300 voters voted for the candidate that they were interested in seeing would win. There were 300 observations. And this time, they were interested in a 99% confidence interval level. Here you get the same information. 165 successes, 300 total people, the sample proportion is 55, your standard error calculation is here, the lower limit is 47.6%, and the upper limit is 62.3%. Because you need more than 50% of the vote to win, you can't really tell by this poll if the candidate will definitely win or not. So what's the big idea? Same as last lecture. Since the sample is smaller than the population, there will always be some level of error in the calculations. Confidence intervals give you the opportunity to establish a range of values within which you have some degree of certainty that the true population proportion exists, or the true population parameter exists. As the level of confidence increases, the width of the interval increases. It becomes wider. This number, this confidence level, expresses how confident you are that the true population proportion is captured within the lower bound and the upper bound. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay? This is your teacher, Torres, saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!